Good evening all, welcome to another RISC-V vid. Now, the reason I'm doing this one is because the last one I did, I've been looking back at it and I didn't really explain things very well or anything like this, what the benefits of RISC-V actually are, nor do they really explain what RISC-V actually is, truth be told. But I have been seeing a lot of misinformation, people not really quite grasping what RISC-V is and how it's important and all that sort of stuff. Because RISC-V is freaking awesome. It is freaking awesome. It really is. There's many reasons for this and I'll get into it. But first, what is RISC? Well, RISC, so basically, what is RISC? RISC is the reduced instruction set computing. So in other words, when you're doing commands with the CPU, you want to move, say, on an Intel chip. Just going to get a smaller brush. Is that? Yeah, that one will do. So let's say you want to move some memory around. You go mov. I think it's mov source to destination, something like that. That's an x86. But what in what is it? But there's more to it. Some of these instructions in the x86, like Intel, AMD, they have all these funky things all over the place. And many things. Same with ARM. ARM has the same thing. I've seen some things that are like 10 characters long. So like there's 10 characters in the command, then at least half a dozen properties after that. And it's supposed to be the same thing. What RISC is you only have the very bare basic commands. The simplest command you can do to do a job, just like the Apollo computer. All their logic sets were done with simple, what's called NAND gates. Oh, did that wrong. Simple things like that. Input, and an output. So yeah, simple NAND gates. Same thing. It's the smallest and most simplest thing you can do. So like, yeah. So what it means is, since we've got reduced complexity, so it's all simple, nice and simple. Where's my mouse go? Ah, there you are. So now we've got everything all nice and simple. We can say one cycle per command. So if I got a whole program of commands going down like this, I can count cycle. So one cycle per command, and sometimes you can have two, which is usually on the branches, but that's it. Whereas like these x86 ones, you can have one command, but that takes like half a dozen cycles. Another one that can take even more. So basically what you're doing is reducing the amount of stress on the system at any one time. So every single instruction doesn't hit the thing, which means reduced in power, reduced power, and reduced power and reduced heat, reduced space. All these things, all these simple things to come in, makes it easier on the CPU because it's not taking so long to go before I can get to the next instruction. But as an adverse effect of this, it does take more commands. Since there is only the basic ones, it takes more commands to do a simple job. So you can have like 6 of them to do a command. So it takes 6 RISC commands to do one command in what's known as CISC, it is known as SC, or complex. So complex this thing here. So in other words, complex instruction set computing. This has been going on since, I think it was like 78. I think 1978 was the first incarnation of RISC. I am not sure. I may be off on that. But the first full-blown RISC commercial product was in the Archimedes, or the BBC Archimedes. A big... Yeah. Then that was in 1988, if I remember correctly, was the first ARM. Yeah. Now, I know there's some people watching this and going, and they're probably about to, looking for that famous, meme saying, RISC is the future, as it was in the 90s. RISC was very big in the 90s. But x86 has won, hasn't it? Doesn't everyone use x86 or ARM for that matter? A big fat, hold on, where's me big brush? Big brush. That is a big fat resounding no. Because x86, the Intel CPUs these days, do not even use CISC. Even though you push CISC to it, even though you're pushing instructions down into the CPU here. Alright, this is the arithmetic unit. So APU, that's right, the APU, arithmetic processing unit. It's basically the brains of a CPU, usually. Something like that. But when the instructions are coming in, say I want to do this and this, what happens is these instructions on Intel and AMD CPUs go into the translator. The translator, the instruction translator, which are then converted into RISC instructions out. So here is RISC. So RISC, and here is CISC. Because both Intel and AMD realized the importance of RISC. So people going, RISC is the future, sort of sarcastic way, and I say, yes, it is. Because that is what's happened in the Intel i7 series, into the Intel i series CPUs, and I think a few before that as well. The AMD Ryzens, they do the same thing. But people are saying to Bastion, well, we got ARM. Why don't we use ARM? ARM is RISC. No, it isn't. It is not RISC. Once upon a time it was. But the new... So ARM 64, so I think it's ARM 64. Got the ARM 64. Last time I looked, I'm trying to think now, I think it's over... The reference manual is over 18,000 pages long. It is huge. And that is certainly not reduced. Whereas the documentation for RISC-V is about 12. Which I think is the original length of the ARM processor initially. So, yeah. It is huge. But then again, Intel and AMD, they're the only ones who use x86. But then again, both use a special brand x86 instruction set, and it is not Intel's. Intel do not use their own x86, which they invented. What they use is called AMD 64. They use the AMD 64 x86 instruction set. Well, AMD did come first. Intel did try with the, It was the x86_64. Sorry, there should be an 86 in there. Sorry. Then the underscore. T instruction set. But then AMD and Intel went to court over it because the Intel one was literally a copy of that one. And like it or not, AMD broke the 64-bit barrier first. So you can say, no, x86 has not won, x86 has actually lost. Because A, no one uses it. B, it is actually using RISC internally. So all your CISC instructions are translated in here and spat out as RISC, which is then done on the processor. See? So it's not exactly a cut and dry thing as you might think it is. But let's go back over to our thing here. But okay, so what is RISC-V? What is RISC-V? RISC-V, this is where the confusion of RISC-V actually comes in, and it is incredibly confusing. RISC-V is a royalty-free, this is critical, this bit here is very critical, and open ISA spec. So it's an instruction set specification. It is not a CPU. It is not an actual processor. It is just the specification for it. Other examples of this are, what was it? Simple OpenGL. So OpenGL is also a simple specification. It's up to the vendors how they implement that spec. It's the same with RISC-V. It's up to the vendors. Another good example of this is the new one, hotness is Vulkan. That is simply a specification, and both these are being held by Kronos. Another one many people may not realize but get equally as confusing is what's called RenderMan. So RenderMan. RenderMan itself is a spec. It is only a specification. What many people confuse it is that with Pixar RenderMan, which is Pixar's own implementation of RenderMan. Other ones that include this, I think, is what was it, Manta? Manta is that. There's even a free and open source one called AQSIS or Axis. So it is only a specification, but the royalty free is key. It is very, very key. What this means is you can use a specification, you can implement it however you wish. You can use it, you can do whatever you want, but you don't have to pay anyone. You don't have to pay royalties to anyone, you don't have to pay exorbitant licensing fees. Like x86's last time I looked, per CPU I think it was like $1,000 per, it's like $1,000 per CPU. So now for a hobbyist or a small business, that's just not going to fly. That's why you don't see many, one of the reasons why you don't see x86 in your phones or your IoT things, because A, the expenses are so bloody high to actually implement them. ARM is no better. ARM is incredibly paranoid about their ISA in their technology. So what you have to do is the same way as like Nintendo and Sega did in the 90s. Say, okay, you want to have some ARM CPUs. Okay, so go on A Cortex. Okay, you want an A Cortex. You want an ARM Cortex. Okay, well that's about I think it's like 500 straight up. But you also have to, like Sega and Nintendo in the 90s with the cartridge-based things, you have to also specify how many do you want. It's not how many you want to actually experiment with, it's how many you're going to sell. Because that is also a cost per processor. You have to put up front the cost right there and then. You can't just go, I want a few. No, you've got to get thousands. You can't go, like I said, you can't go say, can I have like 5 or 6 of them? Nope. You have to order thousands of them. Now, because of all this, has this cost and all that has given rise to other CPU manufacturers or processor manufacturers, like, what was it? It is like, In microcontroller boards like Arduino and stuff, you got processors from Atmel is another one. Many people use that because they're like 10 cents a chip. No problem. You can get them on DigiKey just fine. But because of this cost and all this to do, a lot of people get their own processors from third party like Qualcomm. They do ARM processors and SoCs, or system on a chips if you don't know, and they're in your phones and all that sort of stuff. They are absolute, for lack of better words, pricks. Incredibly closed off, don't offer any drivers to anyone, and they're not very good on the open source front. They're not good on the software front. So basically that's what it is. It's a simple specification, so anyone can build their own CPU. So you can have a tiny little chip that only implements the basic of things, or you can design a huge goddamn whopping chip that implements everything that is in it. Have all these things. You can have one processor core here, you can have some drones off it, you have another one here, and you have some more drones off it. You can have one in here, and then you have all the RAM, which is, so these are all communicating to this processor. These cores, so you can have, that's a RISC-V, that's a RISC-V, and that's a RISC-V core. They all implement the same standards. Whereas you go to things something like a NVIDIA Tegra chip, which uses ARM processors in its SoC. So we've got an SoC here. Basically, you got one core here, you got one core here, you got one core here. They are all ARM, but this one, say, is a Cortex-5. This one is a Cortex-6. There's 1 and 9. And I know I'm getting my model numbers mixed up and all this, and there's another big god or whopping one. But the thing is, each Cortex core has different instruction sets. You have to program each of them differently, and that makes SoCs incredibly difficult. So with this spec, this simple ISA spec, all of these things can now be, so we've got one big chip here. We can have a controller over here, we can have some processing cores here, application cores. You can have your, say, a little memory controller here, you can have your Ethernet controller down here, you can have, I don't know, a crypto one here. All these can use RISC. Can use RISC-V. All of them. So that way you don't have to have special tools for each individual thing. You don't need a different tool chain. You don't need different instructions. You can just have one single implementation. Right there. Boom. Right there. Now with this ARM Tegra chip, this NVIDIA Tegra chip, you've got to pay royalties for that one, that one, that one, and this one. Whereas this one, no royalties whatsoever. Boom. It's free to you to use. The only cost is fabrication. So the only cost you have is the fabrication. So that's why being a spec, a free and open spec that's supported by the RISC-V Foundation, which is really awesome, and they're a non-profit, so they don't do any commercial stuff, so they're not doing risky business with your stuff. It is absolutely amazing. So okay, so that's the beauty of the free and open spec, and why RISC is so awesome like that. But let's get into a little bit more things. So why RISC-V? Why is it? Because RISC-V is simple and elegant. Because it's simplicity, you don't need god almighty huge chips anymore. You don't need huge CPUs. And in fact, because of RISC-V, because of the simplicity and elegant of it, the world's smallest microprocessor has been invented in China and is roughly 2 millimeters in size. 2 millimeters square, somewhere around that. Even smaller than that, I think. It thing is absolutely tiny, and it is a fully fledged CPU. It is a fully fledged microprocessor. Not really a CPU as such, but it is a microprocessor. But also because of the simplicity and elegancy of it, you're going from the smallest one to something that has 511 cores. So it has this big long chip like that. it has 4 here. 1, 2, 3, 4. But then it has all these other drone little ones going and a simple thing in here. It has a big old network of them. So a deep learning network essentially. 511 core CPU, and it is in use. So simple and elegant in the way it does its things. So the simple and elegant. Another one is what's called the dark RISC. The dark RISC processor. The dark RISC. The reason it's called that is because it was built and designed over 4 hours in the middle of the night, in the morning, in the dark hours of the morning. 4 hours. 4 hours to get RISC-V implemented into a processor design. Boof. So the turnaround in your design of your chip is incredibly quick. Another reason to help chip design and manufacturing is because, once again, the simplicity. You don't need to roll out big chips fabrications to actually test them. Since it's so simple, you can design your cores and run them on what's called an FPGA, so a chip on a board, with things like the Vampire 4 and a few other things have what's called a field FPGA. It's called a field programmable logic array. Basically, it's a big chip with a lot of arrays, a lot of logic bits in it. What you can do is when you're designing your RISC core, you can then flash it to this FPGA, this chip, and then you can test it, debug it, everything right there without touching a single bit of silicon. Right there, boom, done. So you don't need to go rolling it out, rebuilding chip like you did back in the old prefab days, even Intel these days. You got to do it. You got to tape out the silicon, get it printed, test it. It don't work. Okay, go back. Whereas this one, you can just go, okay, do a git checkout. So the process would be just do a git pull, flash, CTest, and then result. That's all you need to do. So you can do full-blown automated testing of your processor right there. So git, flash it, run a program, does it work? Cool. Moving on. Doosh. The second point I'd like to make, clean slate. RISC-V has been designed from the ground up. Take it in taking in nothing, taking in nothing, none of the big trends in CPU and processor development or anything like that. It has been designed from the ground up to be proper design. So what I mean, it doesn't have Spectre or Meltdown. Doesn't have these issues because this has all been accounted for because of all the lessons we have learnt over the many years of processor development. So it doesn't have any issue like that. It has better memory management. Better multi-threading, because multi-threading is pretty much specified right into the spec. So what I'll show you, I'll show you here, this is the actual specification document. So let's go, where is it? The memory model. So the base ISA supports multiple concurrent threads of execution within a single user address space. Each RISC-V hardware thread or heart has its own register state and program counter and executes an independent sequential instruction stream. So what that means is you don't need what all these other modern processors have, including ARM, is SMID. You don't need that anymore because it's designed straight into the spec. what's another thing that's been learnt? Well, basically, we know what can be used, what isn't complicated, what is not good, or anything like that. So basically, just lessons learnt. Okay, really. We learnt from our lessons. Yeah, I think that's how you spelled it. Anyway. No, it isn't, but that A shouldn't be there. Anyway. So, the clean slate means we've learnt from our mistakes. And we're building up from the ground up, which you cannot do with x86 or ARM. Why? Because of that is very, very simple. Why is very, very incredibly simple. It is because of that monstrosity. If they break the core, they say no backwards compatibility, we don't care anymore, Windows won't work. And Microsoft will refuse to update it or do anything because they're gods, apparently. And then people's games won't run, the software won't run, and all this nonsense. This also, Clean Slate is also a huge advantage as to why it is awesome. Because it is built from the ground up as a next generation processor. So everything we have learnt. But this is also the reason why it won't RISC may not achieve desktop success unless we do the same thing as Intel does. Intel and AMD using a instruction translator. But then again, you'll need to pay royalties to Intel for doing that. So, or AMD, truth be told. Anyway, moving on. Excellent software. You cannot build a community, an IT community without it. Not only did they make a wonderful spec, they have built the software chain around them. So, like the compiler GCC 9 has RISC-V instructions built in. There is also the, what is it called? Freedom Studio. So you got Free Studio. That has debugging tools built into it for RISC-V and development and stuff like that. Also, not only do they have the whole cool software, they have the hardware to go with it. Now, what else this means in the software? Oh, hang on. We'll go back to Clean Slate for a second. One thing we've learnt over the years is instruction memory map. So, what RISC-V does, it has its own memory map of instructions. So, we've got this huge space here, memory. What they have done is say from there to about here, all of this is reserved. That is reserved for the base and any extensions, any official extensions you want. What this means is that, and this bit over here, sorry, where's the color? Different color. I've got a different color. So this little bit over here, that's for your own proprietary or own extensions you want to put in. That means that if anything changes in here, which it won't, so say the extensions change, then any code built for a RISC-V will always work on any CPU, any processor that is using RISC-V. As long as you target the base, you're good. If you want to target the extensions, generally the G extension, which is a general extension, which is basically a group of extensions, that is also true. So the people who are building the CPUs cannot interfere with this natural thing. So if more extensions come along and they occupy, and so like you got your base and you got your extensions. So if some more extensions come along like this, then it's not going to trample on your work. Your stuff is still going to be fine, and so you can implement some more instructions if you need be for things down the line, and you don't have to recode this bit. Whereas modern day Intel and ARM CPUs, yeah, this is all over the goddamn shop. So excellent software. You got the whole supply chain, and you even got full-blown Linux distributions that are RISC-V compliant. So like you got, so it's like there's an open SUSE build. For RISC-V, there's a Fedora build. And I think there might be an Arch, I don't care. And there is a Debian build. But then again, there's also a Debian build of the GNU Herd. But anyway, so that the software support for RISC-V is already there. It is already being done. And lastly, documentation. There is you got the spec that can be downloaded at any point. So at this point, you can download it any way you want to. Go right ahead. There's also books that have been written. There's also books that have been written by the founding fathers of processors, and it's just actually being taught in school. Schools are now actually using RISC-V as the basis for CPU and processor design. It is not hype. It is actually being used. Okay, so the documentation, books have been written on it, proper textbooks. You can download the reference at any time. You can download the spec at any time. You can download the software. You can do whatever you wish to it. The software has incredible documentation with it. Every board I have seen that has a RISC-V processor in it has extensive documentation. Documentation. You can find it all over the place. So if you want to have a crack at it yourself, go for it. But what I was just saying, it's actually being used. And it is not a fad. It is not hype. It is genuinely, fantastically well designed and excellent marketed and excellent spread. So it is actually being used all over the world. And we'll go to this next one. But is it being used in production? Yes, 1,000 times yes. So China, for starters, okay? China, this thing. China. All the CPUs are now, all their processors that they are producing, all their processors that they are producing are RISC-V. Same with India. They actually have, I think, about 6 of them, or was it 10? They have 6 processors already in production, already been done. Western Digital, they are now putting RISC-V microprocessors in their hard drives. Not just future models, their entire product line. All of them. All existing devices, all of them that they're going to be making, now have RISC-V processors now. NVIDIA, their latest boards now have RISC-V front ends. They now have RISC-V in the front. They're before the GPU. So you got the GPU over here, and you got a little RISC-V controller chip that controls the communications between the graphics instructions coming in and like that. There's one more I forgot to put in here, which I really should have, and that is the big God Almighty. Let's go down a little bit. That is the big, huge thing, which I really want to get. I'll go with a smaller brush. Go this one, which is the Gap 8. What this processor does, this processor is available now for about, well, the board, the Gap 8 Arduino board is about $200. I'm not sure, I haven't really priced the processors, the microcontrollers or processors themselves, but this IoT, it is an IoT processor, has 8 cores. 8. It's an octa-core Arduino, but it's an 8-core Arduino compared to my percent little SI5 that can only run is a single core, but can run at 300 odd megahertz. This is an IoT with 8 fucking processing cores. Not only that, the whole system, all of it, all this stuff, only uses 0.5 watts. All of it. Now think about that. Think about all the heat, the big gigantic heatsink and everything that is on your i7 right now. I have an i7 octa-core and I've got a huge god almighty heatsink, and I'm pretty sure it's sitting at 45 degrees or something like that and sucking in power like there's no tomorrow. This processor, 0.5 watts. That's all it's using. So this, technically speaking, can run off batteries. It's simple. Run off a couple. It's like a couple AA batteries, or even better, this thing could run off a solar cell. A single solar cell, like you see on your calculators that we used to, or sometimes you see them now. There's little solar cells. This processor can run off that, and all 8 cores at full tilt, 0.5 fucking watts. You can do full-blown image, facial recognition, all of that, using only on a battery-powered processor, battery-powered board. Now, the second I get enough money to buy it, I am getting one of these GAP 8 boards, and I want to do exactly that. Do full-blown 60 facial recognition at 120 frames an hour, 120 frames per second, using only 0.5 watts. That's all. The whole board, the whole CPU, all of it, 0.5 watts. That is simply amazing due to the simplicity and awesomeness of RISC-V. So the people saying it's all hype, it's all fat. No, it goddamn isn't. It's just going to take a spark to do it. And people are seeing the benefits of it. Western Digital, Nvidia, India, China. This goddamn thing. So when you look at the big sponsors, one of the biggest ones I'd say there are Sony and Samsung. Both companies who can more than capable of designing a RISC-V processor. Not only design it, they could roll it out themselves. No problem. There's also I think it's called Low Risk project. That is run by one of the founders of the Raspberry Pi. Because the Raspberry Pis nowadays, the latest ones, require a freaking heatsink. They're meant to be an ARM processor, a RISC processor. They're meant to be no heat, no power draw. They can supposed to last for ages, and now it requires a freaking heatsink. What the hell? But yeah, RISC-V is freaking awesome. But anyway, that's the end of my little spiel, I guess. I hope you enjoyed, and I wish to see you all on the next one. If you would like to get some documentation, simply go to just search for the RISC-V Foundation. There you will find the instruction set, references, everything, including a big list of their sponsors. Also, they have somewhat of a commercial arm to them. It's not really directly associated, but they do have a commercial thing. They do the same thing like Blender does, where you've got the Blender Foundation, which just basically holds the copyright and the bank account for donations. That's it. RISC-V is very much the same thing. They hold the copyright for the spec, and they maintain the GitHub, the Git repos, and all that, and arrange the workshops and whatnot. But then they have their own commercial bit, like Blender has the Blender Institute. They do the commercial stuff. RISC-V has the SI5. So the commercial thing is SI5. And while we're here, I'm going to show you something that does make it really cool. So we're going to go to Vivaldi. I'm going to open up Vivaldi as soon as it opens up. We're going to go to the SI5 site. Alright, it's on another screen. I'll just bring it across in a second. No. Oh, bugger off. I hate YouTube. Stop. I hate goddamn YouTube. Alright. SI5. We'll go here. Yes, SI5 home. Alright. You want to go to this website, which is basically the commercial arm of the RISC-V Foundation. So if we go scroll down a little bit. So what we can do, because it is so simple, we go this thing. That's coming soon. The chip designer. But what we can do, we can go a core designer. Let's go design ourselves a core. A RISC-V core. So what basic one do we want? Oh, yes, thank you, accept, thank you very much. So what it means is we can say, what do we need? What kind of core, basic core do we need? So we can say, I want a 64-bit core. So only these ones down here, the E5 and the U5s. And that can run any OS. Or RTOS, real-time OS, or straight up bare metal, or Linux, or just go OS. So basically we've got our things down here. We can't really use these ones just yet, but we can use these ones. So we'll customize a E54 core. I'm not sure what these symbols mean, so I don't know. Anyway, let's customize the E54 core. So we need a new chip. What do we want? What do we want it to do? So what do we want? We want the multiply extension, absolutely. So this is basically showing us what our chip would look like. Yep, I don't want 4-cycle. I would like it to be pipelined if possible for the multiply extension. So, okay, on chip memory, let's have a look. So ECC report, yes, we want ECC, we want error correction. How big do we want our instruction cache to be? 16K seems pretty good. So we can simplify things, we can bring things up, bring things down, stuff like that. Associability, 4-way. I would like that. We'll bring that back up to 16. The data subsystem. We don't have a memory port on here because it'll have its own thing, but I would like to use data cache. So we've got a memory port. So over here we can say I want external memory, either in this core or in the chip itself. And the SoC has its own onboard memory, so therefore we can communicate with that memory. How much memory do we want in the cache? 64K? Yep. And we'll go 4-way again. Right. What ports do we want? So the front port. Let's change this. We want it to be a tile link, because tile link is a open source implementation, free software and open source. If you want to have a look, go ahead. And I want it to be 64-bit wide port. And we'll leave the rest here. The memory port. Oh, the memory port. Oh, you want more channels than that. I want 4 channels, and I want it 128-bit with tile link. That's going to cost a fair bit, but I want 4 bloody channels, memory channels. So the peripherals, the system ports, all that sort of stuff. So we can change the base addresses if we want to. Security, physical memory correction. Thank you. Debug. I want JTAGs. I want some 4 performance counters, please. Interrupts. Yep. PLIC. We want some interrupt controllers. Yep. 16 local interrupts. Branch protection. This is the thing that what Spectre and Meltdown use. So let's go review. Okay. That one. And I'm trying to remember my username, my password. I think it's this one. Is it this one? Indeed it is. So we've got that. So I review all my settings. Here's my whole processor I just designed right there and then. And I can say, go build it for me. I can't yet. So that's basically what I say. I say, I want my core. That's the simplicity of RISC-V. Saying, I want my core. I'm going to design my core how I want it. I say, can you please build me my chip for me, my core for me? And send it off to me. So basically, from what I understand from SI5, they'll say, they'll give you a little test run, say 5 chips, Each chip costs about $5 each. No biggie. So okay, I want 1,000 of them now. So $5,000 for 1,000 custom designed, custom implementations of your own RISC-V chips or cores, truth be told. Anyway, so basically that is cool. That's another brilliant thing of the SI5. Now SI5 is also the makers of that RISC-V board I showed last time. But let's go back to SI5 themselves, because there is another board here which I would love to get. There's a couple actually I want to get. So boards and software. The SI5, that's the one I have, except I didn't get mine in black. I'm quite disappointed. I got green. Aww. But then we have the full-blown Unleashed, which is the RISC-V development board and features U540, which is the one we were talking about, using just back there, or one of the cores. And there's a Linux capable multiple core RISC-V processor. It has 5 processing cores in it. And yep, so let's go have a look. If I buy it, it's if I see this at Crowd Supply, it's about $1,000 for this board, which I would absolutely 100% want. If I had that money, I would buy it in a heartbeat. But there's also another thing here. Down here. This thing. The expansion board. So you see here, this one doesn't have much on it. You have the processor, you have some bits and pieces hanging off it on an SD card. And network, that's it. You got no outputs, you got no HDMI, you got nothing like that. Whereas this one is the expansion board. Basically, it plugs into this. You got PCIe 16 and a 1. You got North Bridge like that. You got connectors. You got what is it? M.2s or M.2 drives. You can plonk them in here somewhere. It has HDMI out, USB, everything. So basically, you can build a full-blown desktop computer using this board and this board. In fact, the Fedora project has about 2, maybe 3 of these, and they use that to build the projects for the Fedora project, build all the packages. So here we are with PCIe support, so you can put in your graphics cards, you can do everything you want with it. Go nuts. Have a full-blown PC RISC-V PC. Unfortunately, this thing costs $2,000, so plus that one, that's $3,000. Bugger. Anyway, let's get back to this. So, once again, thank you so much for watching. Hopefully, this has cleared the air of some things. Why people are going gaga about this thing, including myself. I am a RISC-V fanboy. And, yeah. So, thank you once again for watching. I hopefully did not fluster myself too much. I know I did. But anyway, once again, thank you so much for watching. And I'll see you in the next one. Bye-bye. Oh, and do a bit more research on the RISC-V, would you? Thanks. Bye.